Question 6. Balance the equations for the two stages in the process of extracting copper from rock. So let's have a look here. How can I start with this? Oxygen appears in a lot of the reactants and a lot of the products. So oxygen is going to be balanced last. I can also see that O2 is on its own there. So once I've balanced all the other chemicals, I can balance O2 at the end by looking at how many oxygens I need here to balance up. So I'm going to leave the oxygens to the last. I'm going to start with something that hasn't got any oxygens in it, therefore. Maybe something like Cu2S, maybe something like CuFeS2. Something simple without oxygens in. I'm going to go for this one. I'm going to assume this is a 1. Let's assume this is a 1, therefore. And now I've got 1S on this side, 2 Cus. Let's have another 1 here. So if I put another 1 here now, I can balance the Cus out. I've got 2 Cus there and I've got 2 Cus there. That's got to be a 4. 4 Cus balancing up with the 4 Cus. 4 Fe's now. 4 Fe's on this side and it doesn't appear anywhere else apart from here. So that's got to be a 4. 4 Si's now. Si's don't appear anywhere apart from here. So that's got to be a 4. S's, SO2's here. How many SO2's? 8 S's there. 2 times 4 is 8 S's. I've got 1 S there, so that must now be a 7. And now I've got 7 SO2's that I can balance up the oxygens last of all. So I've got 1 O there and 14 O's, 15 O's, add 12 O's, 27 O's. On this side I've got 8 O's here, so I've got 19 O's in here. I've got 9.5 O2's in there. Let's have a look at this one. Again, copper appears in lots of places and copper appears on its own there, so I can balance the copper last of all. SO2, S's appear here and S's appear here. So let's balance the S's first of all. Let's assume we've got 1 SO2 here, so 1 S here, so I must have 1 S here. And then let's leave the Cus until the end. I've got 1 O there, I've got 2 O's here, so this must be a 2. That means that I've got 2 Cus there, 4 Cus there, I've got 6 Cus on the left, so that must be a 6. Suggest 2 reasons why the sulfur dioxide byproduct of this process is removed from the exhaust gases. Well, if you let sulfur dioxide into the atmosphere, it's going to cause acid rain. Also, sulfur dioxide causes breathing problems and it's poisonous or toxic. Any 2 out of those 3. A passenger jet contains 4050 kilograms of copper wiring. A rock sample contains 1.25% copper, iron and sulfur S2 by mass, CuFeS2 by mass 1.25. So calculate the mass in tons of rock needed to produce enough copper wire, i.e. 4050 kilograms for a passenger jet. So let's assume first of all that I've got 100 grams of the rock sample. Out of the 100 grams of the rock sample, 1.25% is CuFeS2. So if I had 100 grams of rock, 1.25% of the rock is this CuFeS2. Therefore, 1.25 grams out of the 100 grams is CuFeS2. Now, if I've got CuFeS2, how much that 1.25 grams is actually copper? Well, I need to look at the masses of the atoms. The MR of CuFeS2 is 1 Cu, 1 Fe and 2 S's, so that's 163.5, 155.8 and 232.1s, and it comes out as 183.5. Of this amount, 63.5, which is the mass of a copper, a Cu in there, is copper. So if I work that out as a fraction, 63.5 divided by 183.5 is 0.346. That's the fraction of this CuFeS2 rock that is actually copper, around about a third. So 0.436 of the 100 as a fraction, 0.436 is a fraction of the 1.25 grams of rock is copper. Multiply the two together, 0.4325 grams of out of 100 grams of rock is copper. So out of every 100 grams of rock, I'll get 0.4325 grams of copper. I'm going to multiply it up by 10. So 100 grams of rock contains 0.4325 grams of copper. Multiply it all up by 10. 1,000 grams, which is a kilogram, of rock contains, times that by 10, 4.325 grams of copper. I'm going to now multiply it by 1,000. So 1,000 grams, or a kilogram, times by 1,000 is 1 ton of rock. So multiply by 1,000, a kilogram turns into 1,000 kilograms multiplied by 1,000. In other words, a ton, it tells you there a ton is 1,000 kilograms. Multiply this by 1,000, 4.325 grams multiplied by 1,000 is 4.325 kilograms of copper. So 1 ton of rock contains 4.325 kilograms of copper. If I divide both sides, the 1 ton and the 4.325 kilograms by 4.325, 1 divided by 4.325 is 0.23 tons of copper, contains 1 kilogram of copper, because 1 divided by 4.325 is 0.23, 4.325 divided by itself, 4.325 is 1, so 0.23 tons of the rock contains 1 kilogram of copper. I need 4,050 multiplied by 4,050, 0.23 tons multiplied by 4,050, 936 tons contains 4,050 grams of copper. Copper can also be produced by the reaction of carbon with copper 2 oxide. There's carbon, there's copper 2 oxide according to the equation. Calculate the percentage atom economy for the production of copper by this process. Give your answer to the appropriate number of significant figures. Well, what you do is you have a look at the products and you have a look at the mass of the product that you want, which is the copper, production of copper. How much copper compared to everything that I make? So what I do is percentage atom economy is the MR, the mass of what you want to make, divided by the mass of everything that's made, multiplied by 100. So I make 2 coppers. A copper has a mass of 63.5, that's its MR. So 2 63.5s is what I actually want to make, divided by the MR of everything I make, which is the copper again. 2 times 63.5, add a 12, add 2 16s, 127 divided by 171, multiplied by 100%, 74.27 is my percentage atom economy for the production of copper.